Dr. Gopalakrishnan sir, shall we start the session? கேக்குது எவ்வளவு தூரம் பக்கத்துல இருந்தா வர சொல்லுங்க.
டன் ஸ்பீக்கிங் கொடுக்குவா.
பேசவா கேட்கவா விட்ட Dr. Gopalakrishnan sir, shall we start the session? Is it audible? Is my voice is audible, sir? Dr. Gopalakrishnan sir, is my voice audible? Dr. Gopalakrishnan sir, is it audible? Can we start the session?
சார் என்ன பண்ணலாம், பேசாம அவருக்கே போன் அடிச்சு கேட்டுறலாம். நானும் உங்களுக்கு
எப்படியா? இல்ல, என்ன நீ ஆரம்பிக்கவே இல்லையே. இப்ப கேக்குதா பாருங்க. யார் பேர் கேட்கல, யாரும் கேட்கலையே. ஓகே ஓகே. நான் ஆடியோ வீடியோ அன்மியூட் தான் பண்ணிருக்கேன். வீடியோவோட தெரியுது பாருங்க. என் ஸ்கிரீன் தெரியுதா மேடம்? ஆக்சுவலி ஆடியோ தெரியல, செக் பண்ண. யாரும் பேசுறது கேட்டதில்ல. யாரும் பேசலைங்க. அதுவும் செக் பண்ணுங்க. என் வீடியோலாம் தெரிஞ்சது. வீடியோலாம் என்ன வீடியோ தெரியுது. யாரோ பேசுறாங்க கேட்டது. யாரோ பேசுறாங்க கேட்டுச்சு. இல்ல, என்ன பேசுறதுக்கு நீங்க ஜூம்ல வந்து பேசுங்க. நீங்க ஜூம்ல வந்து பேசுங்க. ஹலோ ஹலோ Hello.
Hello, sir.
Hello. Yeah. Am I audible? Yeah. Anyone? Yeah.
Yes, sir. Yes, sir.
Okay. Yeah. Okay. Thank you. Gomadi madam. Yeah.
Dr. Gopalakrishnan sir, is it audible?
Yes, sir. Audible, sir. Yes, sir. Audible. Yeah. I think audible, sir. Yeah. I am able to hear
your
you.
screen, sir, and it is audible, I think. Correct?
Yes. Yeah. I am hearing you, sir. Yeah.
So shall we start the session now?
Yes, sir. Yes. Yes.
So, on behalf of organizing committee of 1 week international workshop on applications of nanoscience in multidisciplinary fields, jointly organized by Department of Chemistry and the Center of Nanotechnology, Priya Maniyamma Institute of Science and Technology, Tanjavur. I welcome the resource person and the participants for this 4th day workshop. This is a time to introduce our resource person. Dr. N. Gopalakrishnan has completed his PhD in 1997 at Anna University, Chennai. After his completion of PhD, he went to Royal Institute of Technology, Sweden for his postdoctoral research. Also, he did postdoctoral research in KIT and AIST, Japan, and also Dongyu University in South Korea. Currently, he is working as professor in Department of Physics, National Institute of Technology, Tiruchirappalli. Professor has published around 100 research papers at the international journals of repute and presented 95 research papers at the national and international conferences. Under his guidance, 8 scholars completed PhD and 4 more are pursuing PhD. He also supervising postdoctoral researchers. Dr. N. Gopalakrishnan has good experience in growth of 3rd to 6th metal thin films by versatile techniques like MBE, PLD, and sputtering. Currently, his research group is working in synthesis of oxide nanomaterials, spintronics, gas sensing, and water purification. Professor has visited Sweden, Japan, South Korea, USA, Hong Kong, Australia, Germany, and Singapore for his paper presentation and scientific discussions and giving lectures. So with his credentials, now I request Dr. N. Gopalakrishnan to deliver his lecture on nano oxides fundamental to devices. Welcome, sir.
Okay. Thank you, sir. Thank you for the introduction. I also thank you. Thank you, sir, for you as well as Dr. Gomadi, Dr. Premila, for giving the opportunity to share some of our work with the participants. Okay. Thank you very much. Thank you, sir. Thank you. Yeah, I given the title as nano oxides fundamentals to devices. When I talked to Dr. Premila, Dr. Gomadi, they said that there is a mixed audience, maybe from research scholars to faculty, that heterogeneous audience. That's why I given the title like fundamentals of devices. So I start from fundamentals, thin film as well as the nanomaterials. Then I end up with the devices. Okay, I prepared such a way that it will useful for all the mixed audience. Yeah, that's why I given this title. Yeah. So slide is not moving. Okay, yeah, so okay. Yeah, today the overview of I think it's hiding something. Yeah. Yeah, the overview today given as that initially I give the activity of our research group, what's going in our research group. So it will also cover the purpose of the conference because as Professor said that 8 students completed PhD under my guidance. So I give the extract of the our group, what we are doing. So overall glimpse of our group work. Okay, it will also cover the nano thin film as well as. Then I start with the fundamentals of thin films and nanomaterials. And the need for, and especially I said that I give the title that fundamental devices. So mainly I consider the device as sensor devices. So need an importance of the gas sensors, then gas sensor fundamentals, and the materials method, the main core here. Yeah, I covered today 2 materials mainly. Yeah, two materials. That is RF magnetron sputtered cadmium doped zinc oxide films for gas sensing applications. This is by thin film. This is covered by thin film. That is nano films. Then fabrication of the chromium doped copper oxide nanostructure by hydrothermal methods for gas sensing application. So that it covers that both the fundamentals of thin films, I said the fundamentals of thin films, as well as the devices made by thin film, as well as the the hydrothermal synthesis of copper oxide. So that it covered for fundamental devices. Yeah. So we'll do the cadmium of zinc oxide. I also compare with the MgO and other materials tuned with zinc oxide. So compare the compared devices. So as I given the introduction, so first just give a glimpse of our work in our group. Okay, yeah. So basically we are a thin film group. So we are oxide group. Oxide mainly working focus on oxides materials, right from zinc oxide to copper oxide, zirconium oxide, titanium oxide, beta gallium oxide, a variety of oxides we work. So mainly on oxide films as well as oxide nano we are working. So we do also work in the nanomaterial. So basically we are working 60%-70% work in thin films, also 40% work also doing the synthesis. So that's why I covered both thin films as well as the nanomaterial. So this fabrication, we do the fabrication zinc oxide combo junction for LED applications. All of us know that the main component of the LED is the PN junction. The main component of the LED is a PN junction. So we just fabricated the PN junction using zinc oxide thin films. That it can be used for the the LED applications. So basically, this is grown by the RF magnetron sputtering thin film. Okay, thin film. So basically, we all of us know that are aware of that. The zinc oxide is generally N-type material because of the its intrinsic donor defect because of oxygen vacancies. Zinc interstitial. So whenever if you grow the thin film, zinc oxide films always gives N-type. If you measure the Hall effect, it will always N-type because of this intrinsic donor effect. So in order to convert this N-type into P-type, we get suppress these native donor effects. For that we use different dopants like aluminum nitride or aluminum oxide or zirconium nitride and gallium phosphide. We dope different dopant in the post material zinc oxide. After that, we convert to the N-type to P-type. So that we get the PN junction. So here is the one junction made by the zinc oxide, aluminum doped zinc oxide get the P-type. Then aluminum doped zinc oxide get the N-type. Zinc oxide is already N-type. Upon doping with the third group element like aluminum or gallium or indium, we will enhance the electron concentration. That's why we dope the aluminum. Even though it is naturally N-type, we also dope with the aluminum or like here gallium, so that the electron concentration can be matched with this P-type material. So we made obtaining the P-type is a big task. I think two scholars, Dr. Balakrishnan and Dr. Gaurasankar, worked in this field. They completed PhD and they left they work in different places. So after converting P-type, can you meet here? After converting P-type, okay, we also grow the N-type layer so that after that we make metallization. Then we check whether this PN junction exhibit diode characteristics. So we check the IV characteristics, then it is really exhibits IV characteristics, so that this PN junction can be used for the further use for the LED application. Again with the aluminum also made P-type. Then we made after that we deposit aluminum zinc oxide N-type layer. Here also gallium doped zinc oxide P-type layer. After that we made gallium doped zinc oxide for N-type layer. Similarly here zirconium used for getting a P-type. After getting P-type, okay, then we do gallium doped zinc oxide N layer. So all are the four PN junctions, okay. After converting P-type, then we also deposit N-type. Then we check whether it exhibits the IV characteristics. A typical diode characteristics. We check that. Yeah. So really we made PN junction, which is the basic component for the LED. Okay. So not only we do that one converting the P-type or N-type into P-type, we also do work in the band gap engineering. That means we know the zinc oxide band gap is 3.2 electron volt. Then we can increase the band gap by suitable dopant. Also we decrease the band gap, a suitable dopant. What is that is called band gap engineering. We are increasing or decreasing band gap. Band gap engineering of zinc oxide being by cadmium and magnesium doping. Upon doping cadmium and zinc oxide, the band gap can be decreased. Upon Mg doped zinc oxide, band gap increases. So look at this. I given the tau plot here. First, in this case of that cadmium to zinc oxide film. So zinc oxide is mainly the band gap 3.35 electron volt. Upon doping with cadmium different concentration, okay, it is decreasing the band gap. We can tune the band gap up to 2.7 electron volt. Then we will decrease the band gap. Whereas the other case, second case, the upper doping Mg, here Mg, see Mg, again the band gap is 3.35. Upon increasing the different doping such as Mg, see we can increase the band gap to 3.44, 3.63, 3.94. So that means we can increase band gap almost 0.6 in electron volt, 0.6 electron volt. Similarly, we can decrease the band gap almost 0.5 or 0.6 electron volt. So what is the application or advantage of the tuning the band gap of zinc oxide? Okay. So after tuning the band gap, appropriately we insert in the zinc oxide PN junction so that the wavelength will be changed. So upon tuning the Mg layer, okay, Mg doped zinc oxide in the PN junction, we can cover the region UV ultraviolet A to ultraviolet B. Okay, ultraviolet B, UV A region, UV B region. Similarly, here we doping the cadmium. Again we cover the wide region. Cadmium cover maybe close to the visible. We know that close to visible. So what is the application of the tuning the band gap in the zinc oxide? So that means that we see the different colors of LED in the outside. Okay, the commercial places or in the buildings or during the festival side, we are getting different colors of LEDs. Okay, yellow, green, blue, whatever the different color LEDs. So all our physics might be here, physics people might be here. We know the band gap is equal to Eg is equal to h mu. Mu is equal to C by lambda. So E is equal to h C by lambda. That means that the band gap varies. Upon varying the band gap, we can vary the wavelength. So wavelength varying means a different color. So obviously tuning the band gap means that we get the different colors. So we outside we see that there is green LED, white LED, blue LED, orange LED. That means that mainly we do changing the technically physics point of view. That we are changing the band gap of the particular material. Upon changing the band gap of the material, the wavelength will change. Wavelength change means that automatically the color will change. That is the meaning. So that is the purpose of the tuning of the band gap and the zinc oxide. So that we can get different colors of LEDs. That is the purpose. Okay. Then, as I said, we also work with nanomaterial as well. Okay. Then effect of we have the copper oxide nanostructure. We have the copper oxide nanostructure. We synthesized by the Rbg method. We use different dopants. We also did the chromium doped copper oxide. Upon doping the copper oxide with upon doping chromium using chromium in the copper oxide, we can tune the morphology. Upon tuning the morphology means that the surface to volume ratio is high. Surface to volume ratio is high means that the efficiency of the device is very high. That is the purpose. The tuning of morphology is upon using the chromium means that okay we can enhance the surface to volume ratio. That is the meaning. So one of the scholar, Dr. Bhuvaneshwari, worked in this field. She also completed PhD. She left and worked in the different places. See, if you look at the here. So actually today I'm kind of the second part, as I say in the overview. Second part I cover this work, so that simply I it here. See here the pure copper oxide is the nano rods. Upon doping the chromium with the 4 atomic percent, the nano rods converted to nano sheets. Then again the chromium doped 8%, nano sheets converted to nano boards. So we get different morphology. Then we made the device. We calculate surface to volume ratio. All this way. Then we got surface to volume ratio higher in this case. So we use this powder. This powder is for devices. So what I shown here, we made a sensor devices here, and that maybe it's at the end. Okay, because second part is mainly covering this chromium double copper oxide nanostructure. So tuning the morphology means that we are the enhance the surface to volume ratio. Okay. What is the meaning surface to volume ratio? That all of it is nanotechnology. My studies but anyway, forthcoming slides I so that one. Importance of surface to volume ratio. Then we do also working the zinc oxide film, not only for the PN junction, we are also working for the gas and application. So zinc oxide based Ag based zinc oxide interdigited electrode sensor by RS pattern. That means we made interdigited like this. Okay, we made thin film sensor out of video silicon substrate. Okay, silicon substrate. We also made a thin film of zinc oxide. Or doping with the different dopant like cadmium, magnesium, or yttrium. We dope. Okay, doped and make the film on this silicon substrate. Also, we found the efficiency of the gas sensing. efficiency. But the efficiency is very low, not very low, it is considerably low. Then we plan for enhance efficiency of the sensor by using the interdigitated electron. So instead of thin film sensor, okay, we made the interdigitated electrode here. Interdigitated electrode, okay, is silver, the silver, okay. Silver, we made interdigitated. Then we deposit film on this IDE, interdigitated electrode. So then we use this structure or this device for the thin film, for sensing devices. This is the efficiency higher than that of thin film sensor. Because thin film sensor, we grow the film here, then we made only contact at the top corner, only two end only here. So the surface area is very, very less. That's why we made this interdigital electrode. Then we made the film here. So the surface area, the covering surface area is very high of the electrode. So that the efficiency is very high. So that's the purpose of the interdigital electrode. So we do compare with the thin film sensor, also IDE sensor. So finally, we proved that IDE sensor is better than thin film sensor. Okay. So that one scholar, Dr. Vinod worked and completed and he left our institute and working outside the institute. Yeah. Just talking here. I think start good. I think. So I am not familiar with Zoom. Anyways, no problem. Okay, so now. Yeah, just talking I know. Yeah. Yeah, then yeah, we do decoct thin film also for the gas sensor, like gas sensor devices. Then we also worked in the transistor method to decoct thin film spin transfer application. That means GMR, TMR, giant magnetic resistance, tunnel magnetic resistance. We are working. Then we do with different transistor metal like magnesium, M1, chromium, vanadium. Okay, we use different transistor method to decoct the films so that we get the films for we try to optimize the condition to get the ferromagnetic behavior like this. Okay, then we use this upon getting the ferromagnetic behavior of the film, then we use it for the GMR or GMR devices. So that the transistor method because for spintronics. You know, the spintronics is mainly used for spins. Earlier people talk about only electronics and photonics. And the people have forgot about spins. So now recent days, this 10 to 15 years, spintronics are the emerging field. Okay, where the people use the spin up, spin up and spin down, read and write. They use for that, even for magnetic storage devices. So the main application of the transistor method because of spintronics applications. That also we are doing both sputtering. As well as in order to enhance this ferromagnetic properties, we also make the capping. That means also the surface functionalization also we make. Yeah. Yeah, we do work with transient but the gas in film as because after making this film also we make the surface functionalization now to enhance the ferromagnetic properties. So from the better magnetic properties, okay, from it shows something I don't know. No, it is a pop-up. It is showing some pop-up. I don't know. Yeah, it is coming on other screens. I get the screen. Yeah, I don't know what's happening. Yeah, it shows some other things. Is it okay now? Is it okay, sir? Now I don't know what's happening. Now it's okay, sir. Now. So, but I guess in the screen, but not my PPT. Yeah. Sorry, Yes. Share. So fine, sir, now? Oh, yeah, I don't see, sir. So we do work with spintronics materials, transfer for spintronic application as well. So one of the scholars, Dr. Shivananda work complete PhD. So right now, Dr. Ms. R.S. Kumar is working this, continuing his work. So two scholars, one scholar completed, another scholar is working in this field. Then we are also working the zirconia oxide nanostructure by co-precipitation method for gas exchange applications. Again, one of our scholars, Dr. Kamala, completed PhD recently and he left. So we synthesize the zirconia oxide nanostructure by precipitation method. Then we make the film by drop casting method. Then we are subject for different gas sensing like ammonia, acetone, ethanol, and formaldehyde, xylene, and different gases we applied. And we see the gas and we just check the gas sensing efficiency of the zirconia oxide. So then, yeah, one more scholar also worked recently, completed PhD. So she left to Dublin, Ireland. Right now she's in Dublin, Dr. Rekha. So she worked in the beta gallium oxide, hydrogen beta gallium for the gas sensing application, mainly focused on the ammonia sensing. So ammonia sensing, and not only for ammonia sensing, we also did for the alcohol gases like ethanol, methanol, acetone. Also, we checked for this material beta gallium oxide, also for ammonia gases also. So please note that the beta gallium oxide is the one of the important material in the recent days. So this material is very. I just focusing more emphasis on this material because this material is very important. The beta gallium oxide, the future it will replace almost all silicon or gallium nitride material, silicon carbide material, because the wide bandgap of 4.9, but a lot of applications or a lot of advantages go over the conventional semiconductor silicon and a common semiconductor like gallium nitride silicon carbide. Because why it is like that means, for example, this beta gallium, actually before that the beta gallium has a 5 molecular person, that alpha, beta, delta, gamma, and epsilon. Okay, among that, alpha beta is a stable form. Among others are not unstable, not crystalline equals not good. So again, alpha and beta is it has its own value, that is monoclinic form. Okay, so among the five molecules, beta is a stable one, and it is lot of advantages application over any other semiconductors. For example, if you compare with actually please see that this material feature it has replaced almost all existing semiconductor material, whether gallium nitride or gallium oxide or indium phosphide or silicon. Feature this will rule the semiconductor industries. I can say that because it's just the figure of merit is almost 3,500 figure of merit, 3,500 figure of merit. Then it has the breakdown voltage very high. The important thing is breakdown voltage is almost 8 millivolt per centimeter. That is very advantageous. So that means it has almost 20 times the breakdown voltage, 20 times higher than that of the silicon, or 3 times higher than that of the gallium nitride silicon carbide. So it has high breakdown voltage. Not only with that one, also it has a figure of merit. Its figure of merit is 3,000 higher than that of the silicon. I think 3,000 higher than the silicon. Also 4 times than gallium nitride and 10 times higher than the silicon carbide material. So it is figure of merit. So it is a lot of advantage. It almost replaces in the future all high power electrons. Maybe the device may replace the beta gallium oxide. Okay, beta gallium oxide. So please note that. So one scholar, Dr. Rekha, worked and synthesized this material. I mean by a Rbg method. And she after making the powder, after synthesizing powder, she made the film by drop cast method, spin coating drop cast method on the interdigital electrode. Again, we made the stamp, interdigital electrode we made on the suitable substrate. Then we made this film. Then it's for different gases like ammonia, ethanol, methanol, and any other gases. So we do work in the beta gallium oxide. This is one of the finest material, the featured electronics material. We are working in this material as well. We work for gas sensing application. It has variety of application as well. Yeah, I can recommend your research scholars or students or faculty here that anyone can work with beta gallium oxide. That means a very good feature. Yeah. So we do work in the polymer membrane. We will prepare a polymer membrane. Okay. this for the water purification. So generally, this is a PS of PVP membrane, polysulfone polyvinyl pyridine. This is a membrane matrix, the pure membrane matrix. Okay, this is generally people who do that PS of PVP. But here we do it differently. We do that. We add the nanomaterial like zinc oxide, Ag or Ag, the nanocomposite. This nanocomposite, we incorporate this membrane matrix, PS of PVP membrane. We enhance the water purification efficiency. That means the permeability or any antibacterial activity, any other activities, we just enhance. So that we just incorporate the nanofillers like zinc oxide. Nanofillers we use nanomaterial. We just prepare synthesis material different. I mean the different method like hydrothermal method or precipitation method. Then after that, this material incorporated the PS of PVP membrane. So in this membrane. So we just compare with the pure membrane with this nanofluorescent incorporated membrane for water purification. So upon incorporating this membrane here, so we enhance hydrophilicity. So hydrophilicity means it will be very attractive water. Hydrophobic means water repellent. Okay, all of us know that. So hydrophilicity, we enhance hydrophilicity upon incorporating this material in this polymer matrix. Then nanopore structure, then high water permeability, allow more water permeability, and also the enhance the antibacterial activity. Right, antibacterial activity. So we just dope the different, we incorporate different nanomaterials in the PS of PVP polymer membrane. We enhance the water filtration efficiency. So one scholar, Dr. Premila, right now she is working at Purification University of Physics department. Okay, she just last complete PhD. Okay, this will submit a lot of publications, work well. Right now she is working there at Purification University. So her work is followed by another scholar, recently joined scholar, the software is following this work. So we are again trying to enhance this efficiency of the polymer membrane with a different dopant, novel dopants. Yeah. So we do work in the material, the graphene like 2D material, muscovite biotite. Okay, this material. So generally, this material mixed with the barium titanate or ferrous materials. Mixed with this appropriate amount, this muscovite material, barium titanate material. Then we just study the multiply properties, just like ferroelectricity or ferroelasticity or ferromagnetic property. We just did the multiply property study. So one scholar right now, Mr. Kriban is working in this field. This field. Then finally, we also work in the phosphor converter white light LED. Phosphor converter white light LED. That means generally we know that the LED, the moment LEDs. Generally, if you got the white LED, people what you do that Rbg is the Rbg color, red, blue, green, and the LED basically they mix in the appropriate ratio. Then we get the white LED. That is one of the technological ways. There is one more the tricky way that we take, so for example, we take the UV LED. Then we put some appropriate phosphor material, phosphor material. Okay, then coat under, then whether UV LED or yellow LED, then we put appropriate material on the surface of the LED. Then we get the white light. Actually, this is similar to that we are truncating or stopping one of the vibrations, one of the emissions. Then we get the white LED. Then got the phosphor converting white light LED. So the phosphor is coated on the LED surface. The already available LEDs. We coat on the surface of the LED so that we get the white light. So one postdoc scholar, Dr. Vasanthi, is working in this field within our group. So the moment when you talk about the white LED, so we should not forget these people. Okay, Akasaki, Amano, Suji Nakamura. These three scientists. Okay, they got Nobel Prize for 2014 for inventing the blue LED. For inventing the blue LED, we know that all of us know that. Okay, 2014. So what is the importance of this blue LED? That because why they give the Nobel Prize for this blue LED means that because already I saw here so already maybe the red and green is already available in the market. The blue LED is not in so long. Though they got the vote in 2000, 2011, 2001 or 2002 the patent and they awarded Nobel in 2014. So this is very important. This is blue LED. This is blue LED. Okay. Because already it was available Rbg, red and green. So that's why the blue is given very important. Okay, so how to get the white LED? That means we mix in the red color and the blue color and green. The appropriate ratio we get the white LED. What I shown is similar shown here. So this is called we call the Rbg method. Rbg red, blue, green. We mix the color and the appropriate ratio we get the white LED. So from this graph, from this figure we can understand. Again we can understand that mixing the red and the green. Yeah, we get yellow. Okay, again, okay, red and blue get some kind of violet or purple color we get, okay, so pink color we get, again we some blues green color, so blue and green, so we get blues green color we get. So this is just color mixing ratio, okay. So I have the opportunity to meet one of the Nobel Prize winners, the Suji Nakamura. So they said the Nobel Prize. Okay, these three scientists. I have the opportunity to meet him during my Singapore conference 2016. I just met him. I have some time to get to chat with him. Suji Nakamura. This person. Okay, this person. Yeah, he is Akasavi. Is Ameno. Is Suji Nakamura. So that's all about our group. Okay, the glimpse of our group. Then fundamental thin films and non-metal will cover here. So we look at the periodic table. Okay, all of us know the periodic metallic table. Okay, there we did that. Okay, look at the fourth group element. We start with the carbon, then we get silicon and germanium, the tin. Okay, silicon and germanium is the fourth group elemental semiconductor. All of us know that. Okay. Then besides these elemental semiconductors, we get the compound semiconductors. Okay, that means 3-phase semiconductors and 2-6 semiconductor. 3-phase semiconductor means that we have third group elements with aluminum, gallium, indium here, and fifth group nitrogen, phosphorus, arsenic is here. So mix this material 3 and 5. Okay, for example, gallium arsenide, or gallium phosphate, gallium nitride. Okay, or aluminum nitride. Okay, aluminum nitride. We mix this third and fifth group element. Fifth group, so 3-phase semiconductor. We get compound semiconductor. There's a lot of advantages over silicon and germanium. Similarly, that the 2-6 semiconductor, second group element, zinc, cadmium, mercury is here, and oxygen, sulfur, selenium is here, tellurium is here. Again, we mix zinc oxide or cadmium oxide or cadmium sulfide. Okay, we get different common semiconductor. Again, these common semiconductors are better than silicon and germanium because of a lot of advantages. So maybe quickly glimpse here. What is the thin film? Because thin film is that the thickness is about, for example, less than 1 micron. 1 micron means 1000 nanometer. The material is thickness is less than 1000 nanometer. We call the thin. Film is nothing but the layer of the material and substrate. We made the layer of particular material. Take then make layer on the particular material. That's called the film. So thin film means that we make layer of material about 1000 nanometer on the particular substrate called as the thin film. Then again, other name is called epitaxy. That is Greek word. Epi means upon, taxis means order. So growth of what is epitaxy? Growth of thin film on suitable substrate. So the structure of the film is continuous with the substrate. Okay, that is called epitaxy. That means we grow the thin film on the suitable substrate, that base material, so that there is a relationship between the film and substrate. That is called epitaxy. Okay. This thin film or epitaxy are more advantages than the bulk material because of it has a lower defects. Then devices made with thin films are small, compact, and more effective. Although the structural, optical, electrical properties are superior than that of the bulk material. So that means that because surface to volume ratio. That means here the bulk material one hand, then same material is made by thin film, then make the efficient, make the devices. Obviously, the device made by thin film is superior than that of the bulk material because the lesser defects or the device is compact, the structural optical variance because of surface to volume ratio is high. Why surface to volume ratio is high means that I'll tell you next slide. Yeah. Just for example, the comparison of the bulk material thin films here. Why do we need thin film? Okay, bulk material. So look at this bulk material. Let's say bulk material. For example, bulk will grown by Sacral's method or some other method. Okay, method. See that. Let's say this is the bulk material. Let's say it's a length, breadth, and A, B, and T thickness. Length, breadth, and thickness. Let's say thickness. Okay. Instead, let's say the L, B, T is equal to. Let's say L and length, breadth equal to T thickness. Then S equal to 6T squared. Okay. Let's say assume that cube of the material. A is equal to B equal to C. Let's say that which is equal to T. Let's say T. Then it is 6 surface area. Okay. We know area is A into B. So the T squared is one surface area. Okay. T, this is T of T squared. Then is 6T squared. The volume is equal to A, we know that A cube. Okay, we know the A cube. Similarly, the T cube, the volume. So surface volume ratio is, see there, surface volume 6 by T. 6 by T, or 6 by T, that's here. Okay. Then we take the same bulk material, we make it cut, make the thin film, come to below 100 nanometer or 100 nanometer or 50 nanometer, for example, thin film. That means obviously we are truncating one dimension, we reduce one dimension. That means thickness is very large. Here we say the thickness is equal to length and breadth, but thickness is almost comparatively negligible here, too small. Okay, negligible length and breadth. So what happens here? The surface is only 2 into LB into LB. Okay, 2 into LB. Then volume is equal to L into B into, we know the A, length into breadth into thickness. Okay, length into thickness, LBT. Surface area. So again, surface to volume ratio is S by B, we get a 2 by T. So here surface to volume ratio is 2 by T. Here surface volume ratio is 6 by T. Here no bulk material. For example, bulk material, for example, if you grow the material of 10 mm or 5 mm, sorry, 10 centimeter, 5 centimeter, for example, grow the bulk material by any one of the crystal growth technique. Okay, let's say the thickness is, the material is the thickness meter 10 centimeter, put the 10 centimeter. So what happens? Surface volume is 0.6 per centimeter. Similarly, if you make the thin film, okay, film, you grow the film by 10 nanometer, let's say 10 nanometer. With T is equal to 10 nanometer, which is equal to 10 into 10 minus centimeter. Okay, you apply here 2 by here, 2 by here, 2 by this T. Okay, 2 by T here. Surface volume is 2000 times, not 2000, 2000. I think it is a 0.6. Here is only 10 centimeter. Here is 10 nanometer. So surface volume is only 0.6 per centimeter only. Here almost 2000 lakhs per centimeter. See, surface volume ratio is very, very high, very, very high. What is the surface volume ratio is very, very high means that the number of atoms available on the surface is very high. That means surface is more reactive. So the more surface is more reactive. That's why the devices made by this thin film is that better than that of the device made by bulk material. That's why people are looking for the thin films. Okay. So that means surface volume is very, very high. The surface is more reactive, chemically reactive. Okay. That's the purpose of making thin film over the bulk material. So again, the thin film are epitaxy just for sake of continuity. Yeah, just for I understand there is some PhD scholar, MS students are in the audience. That's why I made this slide here. So thin film epitaxy it is divided by 2 types: homoepitaxy, heteroepitaxy. For example, the silicon film is deposited on silicon material, we call it homoepitaxy. Or gallium arsenide grown on gallium arsenide, we call it homoepitaxy. Okay. Heteroepitaxy means that the substrate and film will be different. For example, substrate film will be different. So substrate and film will be different. Here is again heteroepitaxy will be made at 2 times: pseudo heteroepitaxy and true heteroepitaxy. In this case, for gallium arsenide grown on gallium arsenide, we call it true pseudo heteroepitaxy. Because one element is common here, gallium and gallium common here. Gallium nitride grown on the gallium arsenide, again we call it pseudo heteroepitaxy. True heteroepitaxy means that the film and substrate will be completely different. For the gallium arsenide and silicon, zinc oxide and sapphire. Okay, sapphire. Yeah, that is the film and substrate completely different. So they call it heteroepitaxy or heterofilm growth. Okay. So this is a different techniques available for growth of thin films. Again, thin films. Okay, that means the thin film growth techniques broadly classified as the solution process and vapor deposition. The solution process, okay, mainly the precursors, the starting materials in the form of the solutions. Okay, solutions. Okay, liquid phase epitaxy, solid technique, spin coating comes under the category solution growth. For vapor deposition, the starting material precursors in the form of the vapor and gaseous form. Okay, gaseous form. Again, this vapor deposition is classified as PVD and CVD, physical vapor deposition, chemical vapor deposition. The physical vapor deposition means the coating process that involves only evaporation deposition of the material on the substrate. That means just physically evaporate the material from source, then deposit the material. There is no chemical reaction takes place. Okay, that is called physical vapor deposition. Physically evaporate and deposit the contents. Okay, but on the other hand, the chemical vapor deposition, CVD forming a thin films on the substrate due to vapor-based chemical reactions. Okay, that means there are a lot of chemical reactions take place, absorption, desorption, surface reactions. A lot of reaction takes place before making the film. A lot of reaction or intermediate reaction takes place. They're called CVD. That means physically just deposit, no reaction takes place. Okay, a lot of intermediate takes place. That's called chemical vapor deposition. Okay. So vapor phase epitaxy, metal organic vapor phase epitaxy comes under the category of the CVD. Because before the film, before final product, we get a lot of reaction takes place. Whereas the multidisciplinary epoxy, MBE, PLD, and sputtering, okay, it comes under the physical evaporator. Just physically evaporate and it deposit the film is deposited on the substrate. Then coming to what's nanomaterial, fundamental nanomaterial. All of them. So I think past 4 days you have been. I mean, the past 4 days you are attending a workshop. Audience, maybe some of the teachers may taught the nanomaterials. Again, for just it's on few slides. Okay, nanomaterials defines the material which have the particle size in the range of 1 to 100 nanometers. Then we say the nanomaterial. It is general definition, basic definition. What is the importance of the material? Why the people are always going nanomaterials? Because early days, 4, 5, 6 years before people are not ever done. So this is 5 to 6 years, people always nanomaterial. Okay, most of the people, most of the institutes, IITs, NITs, other universities, other places, people are always working nanomaterial. What is important? The first category is surface to volume ratio, as seen the thin films. Okay, then new quantum effects will come. The surface to volume ratio means that the surface volume increases. Surface volume increase means that the number of atom available on surface is very high, so the surface is very chemically reactive. Again, the same concept in the thin films. Same concept. Surface volume. So the device is made for nanomaterials is higher, efficiency is higher than that of the compared with the bulk material. Also, significant proportion of atoms are existing at the surface. The suitable, considerable amount of atoms existing at the surface. That's why the nano is very, very important. Or the more makes more chemically reactive because the signification, I say the significant proportion of atoms are existing at the surface because surface volume is high. Okay. Then new quantum effects will come into the picture. The quantum mechanical effects comes into the picture. That means when made material, nanomaterial, the classical laws are the Newtonian mechanics no longer valid. The quantum mechanical effect, quantum physics will govern all its properties. Okay, quantum mechanical effect comes to picture. It determines properties and characteristics. So novel optical, electrical, magnetic properties will get. So because of the quantum effect, the quantum confinement effect comes there. Because the surface volume is high. Okay. So then so the two important feature of the nanomaterial surface to volume basis, the quantum effects. Okay. So this picture shows that where we are now. So the 1 meter, it is 10 power minus 10 meter. So we are between 1 to 100 nano, somewhere here, we are here. Okay, we are here. Nano, I mean the nano. Okay. So why nano structure? Again, I repeat this. That as I said, that it is high surface area, high surface volume ratio. So more reactive and physical loss of bulk no longer dominant properties. The physical loss. Okay, the physical laws no longer dominate. It will not govern. The only quantum laws will govern its property. Physical laws are not valid here. And strength, hardness, conductivity, solubility, and reactivity changes. Okay, all the strength, hardness, all the complete change. Then there is counter bulk material. Even sometimes the insoluble material becomes soluble. For example, some material may be insoluble in bulk form. Then if you make a nanomaterial, then it is easily soluble in the particular solvent. Okay, interatomic distance charges changes. As I said, the insulating compounds become conductive. Even some material insulating compound, insulating compound, it becomes conductive. But when it becomes bulk material, it may be insulating. But when we make the nano, but it may be conductive. Also, reverse is also possible. Some material may be conductive. Okay. Then if you make the nano, again may insulating material. So nano is just change its original properties. Even for example, we know that all of us know the copper is carrying current. Okay, very easily. Okay, current very good current conducting material. So for all of our homes, the current is bringing current is the copper wires in front of home. The copper is a very good conductor. Okay, but same conductor, the copper is very ultra thin film. Make ultra thin come to bring the 3 to 4 nanometer or 5 nanometer thickness. Even the conducting material, copper became insulating material. So because of its novel properties of nanomaterial. Even the inert metal becomes reactive. Okay, inert metal become reactive. The improved strength. When aluminum become combustible. Okay, so that means nano is. So when the bulk material make it nano, okay, it probably completely change because of surface to volume ratio and the quantum mechanical effect. Okay. The same thing I shown here. What are the previous thing I shown text? I shown the pictures. Okay, here the nanometer, the nanoparticle here. See here the particle size is decreasing. We said that nanoparticle when the particle size is decreasing, the particle size decreases, surface to volume is increases. See here, this is the particle size. The spherical particle is one particle. The surface area only 41%. Okay, But again, make the surface particle size small, surface area is 55%. 55%. Again, make further particle small, surface area is 75%. That means what it means, as I said very earlier, okay, the number of the more, see here, significant proportion of atoms existing on the surface. Okay, so when the particle size is decreases, okay, particle size is decreasing, okay, the number of atoms available on surface is more high. For example, see here in this case 2, 4, 6, 9 atoms outside, only 10 atoms only inside, okay, inside. Okay, so the number of atoms available on surface is more than that one. That means that's why the surface is more reactive. That's why the device made by the nanomaterial is very, very superior than that of the bulk material. So again, see surface area, it's an inverse proportional size. Okay, see here, when the particle size is bigger, it is the number of atoms available on surface is almost equal or less than that of the number of atoms inside. But in 55%, when the particle size is small, the number of atoms available on surface is even higher than that of inside the atom. Okay, here when again the particle size small, further small, okay, the number of atoms available on surface is higher than the inside. That's that because surface area is very high. Okay. Okay, so that's the surface more reactive. The same thing as shown here. Okay, this is a square particle, this is spherical particle. So if you count the number of atoms here in this particle, here is less than the number of atoms here. But when the particle is made smaller size, the number of atoms here, okay, there is compare more than the number of particles. So number of atoms in the inside. So number of atoms available on surface is higher in this particle. Okay, that means what I want to really convey that is when the particle size is bigger, that means when you down from the bulk to nano, and even in the nano, if you reduce the particle size further, the number of atoms available on surface is very, very higher because of surface volume is very high. So again, this slide illustrates that whatever said in the previous case that okay. That means the classical when we made the particle as nanomaterials, so the physical laws are no longer valid. Quantum confinement, a quantum tunneling effect, quantum effect comes in picture. This figure again shows the sense of how it's easy to understand. See, this is the classical picture, the classical physics. You know that classical physics. We know that the electron is scared, the electric field is scared. Okay, we know that when electrons hit on electric field, it will be repelled because both are negative or negative charges. Okay, what in the classical physics, the electrons are repelled by electric field as long as the energy of the electron is below the energy of the field. So this electron will be repelled as long as its energy is less than the electric field. Okay, as long as electric field. So that we throw this electron, the electric field just repelled. Something like that. Classical physics is easy to understand. If you take the basketball or volleyball, okay, if you just hit on a tennis ball, what are the ball? We hit on the ball, what happened? It will come to our hand. Okay, come to our hand because Newton mechanics, classical mechanics. Okay, something like the same thing when electron hits on the electric field, it just repelled here in the classical picture. Okay. But the quantum mechanics, I mean, when it comes to quantum tunneling, or when we deal with the nanoparticles or quantum physics, what happens? So if you throw the ball on the wall, it will not come to our hand. Same concept here, because the ball is penetrated, the ball is penetrated to the wall. Same thing here. So when the quantum is, you can see here the electron wall is here, but the barrier is here. Okay, the quantum physics. Okay, just in the quantum physics, the wave function. This is we say wave function. In the case of classical, we say electron. In the quantum physics, we say the electron wave. Okay, in the quantum physics, what happened? The wave function of the electron encounters the electric field. Yes, it encounter just encounter the electric field and pass through this barrier. So it has pass through the barrier, tunnel this barrier. Okay, so that means the quantum physics, the things is completely different. The classical physics, you throw the things, okay, it come to our hand. But in the case of quantum, it just throws, it will penetrate the barrier. Okay, the same thing I illustrated here. Because the first case, here the impenetrable barrier. Then you hear impenetrable barrier. The man is here, the line is here. He is very happy that he knows that line will not penetrate here. Okay, but in this case here, but this here we don't like that. Then the tunneling effect comes here. So the line tunnel the barrier, tunneling effect, quantum tunneling effect is here. So the man ran away. Just so this slide easy to understand the difference between classical physics and the quantum physics, or bulk material with the nanomaterial. So the nanomaterials no longer value the physical law, the classical physics law. So this nanometers may be prepared by two methods. Okay, a top-down approach and bottom-up approaches. Okay, in the top-down means the ball milling, lithographic and etching, and I mean the bottom-up approach is inert gas content pulse related deposits, sputtering, molecular method. So here we have the nano. Here nano. So many people need to understand that nano is lower than the atomic level. Not like that. Okay, nano is higher than the atomic level. Okay, atoms. So here is the nano material. Either we can make the bulk material, make a small cut, make it the nano material, or we assemble the atoms. The atom is here, we make clusters. Then we build the atoms. Then we can get the nano material, because nano material size we give the 1 to 100 nanometers. So upon assembling the atoms, we can get nano material, or cutting the bulk material into small, we get nano. So that is called top down, the bottom approaches. That is what I found here. Okay. So then we come to the gas sensing, need for gas sensing. Yeah. But how long is your time? Another 15 minutes maybe. Yeah. Gomadi madam. Hello. Yeah, here is that how important of the gas sensor, need for gas sensor, avoid industrial production and medical application, environmental applications, indoor quality, automotive industry, lot of applications gas that, I mean the gas sensors. Okay. When you look at the industry, a lot of smokes are here, a lot of gas leakages there. Okay. So we have to monitor this gas leakages or the pollution. We have to monitor the pollution. That's for that purpose the gas sensors are very useful. Yeah. Even automobile also, there are a lot of gas smokes comes out. Okay, this automobile. So all of us, we would not forget the Delhi pollutions. Okay, the December, November, a lot of smokes. Okay, the Delhi pollutions. Okay, yeah. This slide I just picked from internet. Okay, Delhi. Yeah. Then again, the one more important application of the gas sensing is the alcometer. You know that when the people are drunk and drive, the people are actually caught by police. Actually, there is actually sensor devices. Okay. So where that upon the blowing the man, there is change in the physical parameter. That's the normal moves here. So algometer is nothing but again the gas sensor. Okay. So there are a lot of physics maybe we see together. That means initially that means that algometer or gas sensor is calibrated with the air ambience or some standard material. So upon exposed to the gases, so alcohol gases, or ammonia gas, any other gas, ethanol, methanol, any gas, or some people are drunk. Okay, if you take drinks. Okay, so blowing on the sensor, what comes there is a change in physical either conductivity or resistance or mass. What anyone can change. Upon changing this one, the real people is drunken or whatever thing. So that there is a physics behind that. Really, the police found that that man is drunken. Okay, that means that the sensor really observe that order or gases, then there is a change in parameter, so that people find that he is really drunken. Okay. So alcometer nothing but again the gas sensor. Okay. So this is notable gas leakages disaster. Okay, gas leakage, gas disaster in the China 1942 and in 1921 in Germany and France 1996 and in India also Bhopal in 1984 when we are child Bhopal gas tragedies that occurs. Okay, because what I want to tell you, the gas leakage is very very dangerous one. Yeah. I'm stucking then and there. Yeah. You're stucking again. Hello? Yeah, before the device sensor, okay, what is sensor? Sensor is a device that converts one physical parameter to another physical parameter that can be conveniently and accurately measured. Okay, that's a difference, typical definition of sensor. That means actually it converts one physical parameter to another physical parameter. That means in the undergraduate books. Okay. I said that is the algometer. Okay, upon the man is blowing on the sensor, okay, it may the resistance may changes or any parameter, one of the parameter changes, that can conveniently measure. Okay, that is the basic concept sensor. The device that convert one physical parameter to another physical parameter that can conveniently and accurately measure. This is called the sensors. Okay. So the sensor is a receptor and transducer. All of us know that. Okay, the receptor transforms the chemical information in the form of energy, and the transducer convert the energy into useful signal. Okay, electrical signal or energy signal. Okay, so convert. So if you see here the different things, what are parameter changes? For semiconductor gas sensor, electrical conductivity changes, and other FEDC gas sensor work function changes, and physical sensor mass will changes. That means okay, upon exposing different gases or expose different environment, so one physical parameter changes. Okay, either electrical conductivity or work function or mass or effect or a heat effect, heat, what are things will change. Okay, that we can conveniently accurately measure. There is different type of gas sensor. What is physical parameter changes? I summarize it here. The important parameter gas sensor sensitivity, stability, and selectivity, response and recovery time. Sensitivity means the change in measurement signal per concentration unit of the sensor of the gas slope of the calibrated graph. Okay, sensitivity, change in concentration, per concentration. So change the signal per concentration. Okay, they usually get it from the slope of the graph. Okay. I actually given a sensor response here, sensor is here. Okay. Stability means that, okay, after ability of sensor to provide reports of results for certain period of time. Stability means that suppose we had February device today, what will happen 2 months, 3 months, 4 months, or 1 year, where how was stability? Whether it gives report results or the results are decreasing, or the device quality decreasing, okay, diminishing. That is the stability. Okay. Selectivity means that the particular device can observe good for the particular gas. That is the selectivity. Response time means that how quick the sensor responds, okay, upon exposed to gases. Okay. Recovery time is how quick come down to the best level. This is called recovery time. The sensor response, okay, given here, okay, RA minus RG minus RA. RA means that, yeah, sensor, yeah, RA means that resistance of the air. That means that before we measure the gas sensor, instead we measure the resistance of the particular device in the air ambience. That means just air ambient. That we measure the resistance. That we measure the resistance RA. Then upon exposing the gas, whether ethanol or methanol or acetone on any other gas, there is change in the resistance. Okay, that's called the RG. The difference in resistance divided by original resistance. That's called the sensor response. Okay. So that's what happened. That is what happened. Okay, that is what is the difference here. Okay. Then upon exposing the gases, there is change in resistance here. Okay, change in resistance. That will conveniently measured. Then it is quantified. The sensor response. So basically, there is a change in resistance or conductivity that we quantified. Then we measure gas sensor response. Okay. So again, yeah, this is not necessary. Yeah, some literature. So then the first part says the zinc oxide material. Okay, we use for thin film. First case, thin film grown by the RS background part of gas sensing application. So zinc oxide has a lot of advantages. Okay, I just say here the properties is N type. As an N type, the band gap 3.37. The hexagonal word structure. So it is A equal 3.24 Armstrong unit, and C is because 5.207 Armstrong unit. The higher binding energy, the exact binding energy, and higher melting point. This is some of the physical parameter of the zinc oxide. Okay, this material, as what I was shown previously, we use it for electronics, optoelectronics applications, electronics applications, gas sensor applications, a lot of applications. Either thin films or nanomaterial, we use it for different applications. Okay. Essentially, I just focus on the cadmium doped zinc oxide thin films, okay, grown by the RF magnetic sputtering. Initially, we made the target, cadmium zinc target, different target, for example, 3, 10, and 20. Okay, this is pure zinc target. We also made Mg doped cadmium zinc oxide, different doping, 3 and 10 and 20 mole. Okay, initially I focused on this first one. Okay. Pure and cadmium doped zinc thin film. Okay, same thing. I did not extend this because they will repeat one. So initially we made this target by ball milling. Okay, ball milling, mixing the dopant with the host material zinc oxide, ball milling. Then okay, we make hydraulic press it, and we want the pellet. We got this pellet. Then we kept this pellet in the furnace. Okay, then it became solidified. We got the target. So this target, we got this target. So this target we keep in the RF manganese sputtering. Then okay, RF manganese sputtering, the acts as a cathode as anode. Okay, then we just bombard this this target by the argon, highly energetic argon gases sputtered. Okay, argon gases just sputtered, just bombard on this. This target. So the atoms or molecules from this target, okay, knocked out and deposited on the, the substrate here. That's we made the film here. That means first we made the target, kept it in the aromatic sputtering, then we bombarded the energetic argon gases, the atoms are knocked out, and the films are deposited here. So then this ground film is subjected for a different characterization. Okay. Similarly, we made for magnesium and also for yttrium also. First we had the magnesium. So I don't want to repeat this one. After making this film, this magnetic film, this are sputtering unit which I have in my laboratory. So here, see here again same picture here. Okay. The magnetrons here. So atoms from here. Target is okay. Not deposit as a film here. Okay, this film, okay, we characterize here. This is a gas sensing setup. Okay, where is the gas? After making the film, our device we kept it here. Okay, this inlet, we send the gases here. This outlet of the gases here. Then this our film is here. Film is here. Then we made the electrode here. The electrode is here. The electrodes connected to the Kittel electrometer. That means Kittel electrometer. Then that means what are the change in resistance which we measured here. Initially, as I said, okay, we measured the resistance, the air ambience area. Before starting the experiment, we measure the resistance of the film in the air ambience. Okay, that is the RA. Then we send different gases for different concentration. After sending the gases, there is upon fall on the gases here. Okay, there is change in resistance. That resistance we measured here. Then we calculate the sensor response. Okay, using this formula. Okay, this formula. Okay, this is formula. There is okay. This formula. So the change in resistance, okay, with respect to different concentrations of the gases or different temperatures, also we can be able to measure. As we are heater is here, we can measure different room temperature, 100, 120, any temperature we can make. We can set the temperature of the gases effect also here. So first part, this is the cadmium doping oxide film. So we take XRD. Then we confirm that film is the single crystalline film with 002 preferential orientation. So really it has the hexagonal Fourier structure. Then we measure using the Debye formula. We measure the crystal size. Okay, for different doping concentrations we measure here. Also we measure Hall effect. We measure different resistivity, mobility. We also measure the Hall effect. Then we categorize the film. Okay. Then also we made the top plot. We use measurement. Okay. As I said, this is the pure zinc oxide is here. Upon double cadmium, the band gap decreases. Then we found the different defect levels in the. We measure the photoluminescence. Okay, we grow the films and subject photoluminescence. We get the yellow band, green band, blue band. All this effect. We also studied the effect of doping on these different defect levels. Okay, yellow band, green band, blue band. This may be attributed to the oxygen vacancies, zinc interest here. Now, how upon doping, how these defects are suppressed, or how the intensity changes, this always studied. That is supported by gas sensing results. Okay, so whatever the characterization we did finally justify with our gas sensing results. Okay, then this is the gas sensing response. Okay, this was the gas sensing response for the this is that 0 means pure zinc oxide only. Then 3 and 10, 20 modes. What I already defined here, actually, here, okay. Yeah, here I shown here, yeah. 3 mole cadmium dopant CZ03, CZ10 means 10 mole cadmium dopant thing, CZ20 means 20% dopant cadmium film. That is what I shown here. So here I shown here for the different for different temperature, for different doping control of the gas response. So for ethanol gas here, and for methanol, we saw the response, gas and response here. The ammonia gas also we saw here. So maximum response we got the 89%. Okay, for ammonia here, and here got the almost 130% here, 130% for the methanol. Okay, for 20% dopant, 20% made this one, yeah, green one, yeah, green one, 20%, green one. So here again, the 123% of this 20% doped cadmium zinc oxide then film. Okay, what I want to tell us is the green is pure zinc oxide is here, pure is here, pure is here, pure is here. So upon doping with cadmium, we enter the gas ability. That's what I want here. So the red one is the pure zinc oxide. Other colors are on the different dopant concentration. So for the particular temperature or particular dopant concentration, okay, the maximum sensor response of time. Anyway, as a sum that the gas sensing efficiency enhanced upon doping with the cadmium. Again, we found that the response and recovery time. Okay, response recovery time we found here. Then we give scientific explanation why. Okay, because upon doping, maybe most of you may refer my papers. We give more scientific reasons why it happens. So upon this is here with the air ambience, the barrier. But the barrier is very high. Upon exposing the gas, okay, the barrier is less. See, the potential barrier is very less. That's why the conductivity resistance will change. So that is the method by the electrometer. So more scientific, for more scientific, you can read our paper. Okay. So upon exposing gases, there is change in the potential barrier. See, without gas, with gases. So that there is a change in the physical parameter. Okay. So this is for Mg magnesium doped zinc oxide film. So I don't want to repeat the same thing. We must see here. This is pure one. Okay. It is pure one. So black and pure one. Some cases upon even there more dopant concentration also reduced. So for optimum concentration only the gas sensing efficiency is very high. So in this case magnesium. So for first two cases the gas concentration increases. Okay. And third cases. Okay, the sensing efficiency decreases. However, here we get the enhanced efficiency upon doping with magnesium. Yeah. So we have a summer. Yes, here. Okay. So again, we made response recovery time. So we made some bars here or here. So finally, I saw the end. So then whatever shown here, only thin film sensor. In thin film sensor, that means we deposit film on the only simple substrate. Then we made the sensing response. But we feel that efficiency is very less. Then later in enhanced things, okay, we made interdigital electrode, IDE pattern. Okay, that we made by electrode. Okay, Rbg Method. That means this pattern we transfer to our film, our substrate, for example. Yeah. See here. So I can say here. Okay. So this is the interdigital pattern. Okay, this pattern of the length and breadth is shown here. So this pattern will transfer to the first one of substrate. Then we made the film. For example, shown here is here. This is silicon substrate. This silicon substrate. Initially, first case, whatever is on the graph, we made film, the whole film on the substrate. Then we take lead here. We take lead here. Then we made the gas sensing. The gas sensing study. Okay. Then the efficiency very because surface area is very high because we made only electrode here only we made electrode here. Okay. But we get the film on the whole surface, whole area of the substrate. But in this case, okay, we made the electrode. Okay, the electrode. Okay, the electrode. Okay. First we transfer the pattern here. Okay. Using suitable mask, using this mask, okay, using the DC magnetron sputtering. First, this transfer this pattern on the substrate here. Then we made the sensing layer here. Previous case we made this film only and directly on substrate. In second case we made interdigital electrode. Then we made the film on the IDE substrate. Because there is a lot of area, surface electrode. For previous case only made drop only here, simply drop here. Case surface area is more high. That means the electrode surface area is very high. Then upon making the sensing efficiency here, if we expose the gas here, then the efficiency is more higher. That means we have to manage the sensing sensor device using this interdigital electrode device rather than the previous thin film sensors. So we expose different gases as like in previous cases. Then we measure the sensor response. We found that more efficiency, more response than in this case than the previous case. Whatever I shown here, in this case, all these cases, okay. So I finally could come here. So then finally we made the 3 devices, which has been picked from the each one of the series. cadmium, we picked cadmium, one film from cadmium double film, zinc oxide film, one from Mg double zinc oxide film, one from Mt double zinc oxide film. We made best film we picked, then we make the film, we make the device, okay, we make the device, we make the film on the interdicted electrode. We made the film on this. That means the best film of the cadmium, best film of the magnesium, best film of the yttrium, we deposit on here. Here, then we finally compare. I show some of the histogram here, okay. So finally, this is the things I want to talk about. So this is a gas response compare thin film and IDE sensor. This is the first case, whatever I shown here. If we simply make the film on orbital macron sputtering, okay, on substrate, silicon substrate, then we measure the efficiency, okay, the gas efficiency. Then second is IDE sensor, okay, after measuring whatever I shown that, this one, okay, this one, okay, this one, okay. So we compare both thin film sensor, IDE sensor, we can see very well see here. This is cadmium, this is magnesium, this is yttrium film here. You can compare, you can see here, the first case. So here for case, the ammonia for this ammonium sensor sensing for 50 ppm concentration. Okay, sensor gas sensor respond only 89. Here we got 93. Okay, here 92, we got 99. Okay, 97, 103, 104, 112. That means the IDE response is very higher. Again, with this Mg, here again here 43, 56, 48, 63, 86. Again, the yttrium, see here, yttrium. So the if you compare all these values are higher than that of this thin film sensor. That what I want to emphasize that the IDE sensor is the more efficient than thin film sensor. So even then, all these films are only made in the prototype devices, not made in clean rooms or any other lithography facilities. Even then, in this case, we showed that IDE sensors are better than thin film sensors. Okay, that means if at all we want to the sensor devices, it is better to fabricate device based on IDE rather than thin film sensor. That because our surface area is very because we made interdigital electrode. Okay, yeah. See all this sensor response is higher than that of the corresponding thin film sensor. That is what I want to emphasize that one. Yeah. See again the response recovery time. So response. Say in this case, maybe only in this IDE sensor. So in this case, see here, yeah, only 83. Maybe here, yeah, maybe low, little bit low here. Yeah. In this case, maybe little bit low here. Yeah. And then in this case, this is 95. You have 102. Okay, 102, 49 and 58. 302 and 412, 123, 152, 110, 101. So two cases that are almost more or less equal. So response recovery time only. Yeah, that we are justified using our results justified already. So that was the overall summary. That means that the IDE sensor is higher efficient than the thin film sensors. Then second case I use a copper oxide nanostructure. Okay. Previous case with thin film sensor, case where the copper oxide is synthesized by the, we will take another 5 minutes, 10 minutes finish of it. Okay, we made the copper oxide powder synthesized by the hydrothermal method. Okay, this is the flow chart of the copper oxide synthesized by the, by hydrothermal method. The copper sulfate and sodium acetate hydrate, we taken the precursors. Then we follow this flow chart. Okay. Then finally got as a copper oxide nanostructure. Then same thing. Then pure copper oxide. Then we use it for the chromium doped copper oxide, as you saw in the previous slide. The first, second, third slide. Okay. Then chromium chloride. Here we have chromium chloride here in this precursor. The chromium chloride appropriate concentration we ordered. Again, we follow the flow chart. Okay, I follow the flow chart. We get the chromium doped copper oxide nanostructure. That means we doped the 4 atomic percent and 8 atomic percent chromium in the copper oxide host matrix. That means we were pure and 4 atomic percent chromium doped and 8 atomic percent chromium doped copper oxide nanostructure. We got it. We follow the simply hydrothermal method. We got the powder. Okay, then we made the different characterization. I don't know so here. This is to be hydrothermal setup here. Okay, here autoclave. Okay, here this is autoclave. Okay, what are the solutions? See, the solution kept in Teflon autoclave. What are the solution? This solution prepared. So the prepared. Okay, poured in the Teflon autoclave. Okay, Teflon autoclave. See what I saw here. Teflon autoclave. Okay. Transfer Teflon autoclave. So this here, okay, this autoclave is kept in the furnace of appropriate temperature. What I was shown here, see, kept in the autoclave for 160 degree for 12 hours. Okay, then the copper particles are deposited, precipitated here. Precipitated here. That we okay, then washed with the distilled water ethanol. Finally dried at 60 degrees. Then we get the copper nanostructure. Just we follow this flow chart. That means the precursor solutions are kept in the autoclave, poured into autoclave, then kept in the kept in the furnace at the temperature of 160 to 12 hours. Okay, then after that we got some particles, powders here, we deposit here. Then we take, yeah. Distill, we wash the precipitate with distilled water and ethanol. Finally, dried at 60 degrees, we got the copper nanostructure. Then we subject different characterization. This is our XRD. We also with P1 and 4 chromium dope and 8 chromium dope. Okay, we also given the explanation why it is changes, why the characterization changes. We give very good explanation. Then we follow ritual refinement. We measure the latest parameters. Then, yeah, this is important thing. What this slide shown maybe at the very first. Okay, so this is all the pure copper oxide. This is all 4 atomic with the chromium dope. This is 8 atomic % chromium dope copper oxide. See, first case nano rods. This is nano rod. This is a different magnification. This is different magnification. This slide I already shown. Okay, earlier, yeah. So this first case we get nano rods. Second case the 4 atomic we get nano sheets. In the third case, we got the nano boards. That means we change the morphology. We change the morphology upon doping with the chromium. So we have nano rods, nano sheets, and nano boards. Okay, nano boards. Okay, nano boards. Then this slide summarize. See here. This slide summarize here. Pure case we get nano rod. The surface area only 3 m squared g. And in the second case, nano sheets. In this case. Okay. In this case, nano sheets we got upon doping with the chromium 4 atomic %, we got 8 m squared by g. And third case, yeah, the third case, nano boards. Okay, the morphology is nano boards. So we tune the morphology 16 m squared per g. Okay, we get the dimension of the given here. That means the third case, that means we tune the morphology. Upon tuning the morphology, we get a surface area square. Why surface area? What already we discussed in the fundamentals. When surface volume is very high, obviously what happens, the efficiency is very high because the surface is more reactive. The number of atoms available on surface is more higher. That's why we used this film, the powder made by in this condition. That means 8 atomic mole % doped copper oxide used for fabricating the gas in the flames. Okay, yeah. So because surface area, we proved surface area very high. So we used this powder. Yeah, I mean this powder. Yeah, nano powder. So this also we made. Yeah, after making the copper synthesis powder, we make the film. Okay, by drop casting method, spin coating method. Then we measure the gas sensing response for different concentration of the different gases, for methanol, ethanol, and ammonia made, and we give just right here. Then this is thin film sensor. After synthesizing the powder, we make the film and we measure the gas sensing efficiency. I give a summary. The same summary here. And after that, same thing we made the screen print technique again. ID sensor here. As in the previous cases, okay, here. See here, yeah. We need the copper oxide powder from hydrogen process. Okay, for whatever the using the hydrogen process, take the powder, then nano sheet powder. The third one, 8 atomic doped chromium doped copper powder we take. Then we mix it with the PBMA. It is kind of some binder, and with the BCA, butyl carbonate acetate. This is under it is a solvent, some solvent. Okay, we mix this copper oxide powder with some binding agent and solvent. Okay, they make them. We got some kind of paste. Okay, paste. Then again we made the IDE, the interdigital electrode. Okay, interdigital electrode. That's the previous case. After making interdigital electrode, then we paste this film. Okay, they paste the film on this electrode. Because we already showed that IDE sensor is a higher efficiency than conventional sensors. Okay. So in this case, we made a substrate, instead of we made a PET, polyethylene nitrate. See, I got a polyethylene tetrathalate. Okay, PET substrate color. This substrate is more flexible. Mostly we can bend. Okay, we can make the very ultra fine sensor, the flexible sensor. Whereas previous case sensors it is more rigid. Okay. So this is a flexible sensor. Nowadays, the market there are a lot of flexible sensors. Please note that all of you please note this. Recent days there is more marketing for the flexible sensors, because this flexible sensor even we can paste in our house curtains, or paste on the walls. Okay, even anywhere we can convenient place we can paste this flexible sensors. So in this case, what we made that this interdisciplinary electrode made on the PET substrate, polyethylene and tetraethyl with the flexible substrate. We can bend. Okay, see, we can bend here. Then we made interdisciplinary electrode. Then we made the paste. Okay, the copper stencil line, or the prepared by this method. Okay, PMMA, PMPA, and BCA. This paste deposit here. Okay. Then so that this gets deposited by the screen printing technique. Maybe we use this facility at the Warsaw, the Poland. We use the Poland. Okay. So what I want to tell you is that we made IDE structure on the PET substrate, and we made this copper oxide nanofilm. Okay, bromide double copper nanofilm. Okay, nano powder thin film. You can say that. Okay, that's not here. Okay. Then we measure. Okay, yeah. Again, we measure all the parameters, different ethanol, methanol, acetone, or ammonic acid. We measure gas sensing efficiency, and we compared with the conventional gas sensing. Okay, again we showed that the sensing efficiency in this case is higher than that of the previous cases. See here, our sensor is more flexible, because PET substrate here. The same thing what is shown here is again showing here. Sensor, okay, more flexible sensor, and we made the sensor response even after before bending, after bending. So after we kept pending for some time, okay, or sometime pending for 15 minutes or 20 minutes or 1 day, we bend the sensor, like this. Okay, we bend it and keep it for some time, or some day, or some hours. Okay, some hour. Then we check the efficiency. Okay, check the efficiency, get the efficiency. See here, almost. See here, almost. So before bending is here. See here, before bending almost here. After bending, so different. So almost the black points are here. The measure see here. So there's no difference between the before bending, after bending of the sensor. That means our chosen substrate is very high. Our chosen method is very correct. Okay, our sensor not damaged after the bending. That is an important point. Our sensor is efficient not less. Our sensor is not damaged after the bending. So before bending, after bending, almost the sensor response is almost same, almost equal. So that shows the stability, not stability, rigidity of our device. Okay. Again, the sensor response here. See number of weeks: 4 weeks, 8 weeks, 12 weeks, and 16 weeks. So almost 4 weeks, 8 weeks, not much difference. After 16, 8 weeks, there is a change in sensor response. So because after we made the device, okay, is screen printing technique, not in the clean room or not in the facilities. Okay, even then it's not much difference in the sensor response. Okay, before bending, after before bending, after bending, a number of weeks here. So if you look at the horizontal wise, okay, number of weeks, okay, number of weeks, even only after 16 weeks is slightly decreases. Up to 8 weeks, the efficiency, up to 8 weeks, not much difference in sensor response. But after 8 weeks only, before bending, before and after bending, there's slight decrease in the efficiency. Okay, gas sensor response. So that we have to sort out. That means we have to that problem we have to sort out. Yeah. So with this, I stop here. Thank you very much for giving the opportunity. Yeah, thank you very much. Thank you, sir. Sorry, I took some more time. Extra one, I think 15 minutes, I think. Sorry. Any speaker is following me. I continue this time. There is one more talk after me, sir. No, is there any talk after me? Is there any talk? Oh, sorry, I continue this time. Sorry. Okay. Thank you, sir. Thank you, sir. Thank you. Sir, someone maybe send me a mail if you have any query, any questions. Yeah, you may post me and I will reply to you. Yeah. Yeah. Okay. Yeah. Thank you.
please. Ada kamarnya orang itu.